So obviously, Robert's not going to be able to cover the full range of this topic, but he can give you some basic information, and then Robert's available, I'm sure, at any time to help answer your questions if you need more in-depth help. So I'll introduce Robert, but first I want to just quickly go over the WebEx and how it works. You should not have to do anything until you want to ask a question. So you should be able to just sit back and watch the slides, and they'll progress on their own. And Robert will speak into the phone, so you'll be able to hear the audio. If at any time you have any problems, you can go down to the lower right-hand corner, and you'll see there should be a chat box down there. And you can see the line send to. If you have a technical issue, you can click on that menu there next to send to, and you can page down until you find who's my guy. I'm blanking on your name. Brian. I'm sorry, Brian.
Weaver listed.
Are you on there? Oh, Brian would be the host. Is that right, Brian?
Yeah, just send it. If you want to send a message to me with a technical question, just send it to the host.
So you can just send a message to the host, and Brian will help you out with your technical issues. And also, if you have questions at any time, you can also type those down in the text box down in the lower right-hand corner, and you can send your question out to all participants. That's fine. You just hit the return, and it will send that out. And then Robert will be keeping an eye on those, and I will too. And if we need to interject, we'll toss in your questions. There will be time at the end also for question and answer. So that behind us now, I want to introduce Robert Mullen. He is an assistant professor here in the School of Environment and Natural Resources at The Ohio State University, and he's stationed in Worcester. So if you want to meet with him, you would need to go up to Worcester to do that. Robert has his PhD from another OSU. It's the Oklahoma State University, and he specializes in nutrient management. And what I like about what Robert does is he's working both sides of the coin. He's trying to help farmers maximize the efficiency and economic return of nutrients, and at the same time minimizing environmental contamination. So manure management is one of those areas that Robert works in, and I'm going to let him get to his presentation. Robert, it's all yours.
Well, Joe, I certainly appreciate it, and I certainly appreciate the opportunity to interact with the group. This is about the third or fourth webinar that I've done. They usually go off without a hitch, but God forbid something happens, Brian or Joe, and you lose me completely. Just send me, hopefully I'll still be logged in on the text, on the actual WebEx presentation. You guys can catch me and make me aware of something that may have gone wrong. Just to give you a little bit of background on what we're going to be talking about this morning, and Joe did a really good job of introducing me. I do kind of play both sides. I do have an extension appointment with Ohio State University, so I work pretty closely with a lot of farmers throughout the state, and more specifically, a lot of the extension educators that occupy the county positions that have more face-to-face interaction. They're sort of a go-between between myself and the producers that I do interact with, but I do interact with some directly. And I primarily talk about nutrient management more from an agronomic perspective of doing a better job of supplementing nutrients for crop production. I'm a huge fan of improving efficiency of use, not only from the economic perspective, trying to help a producer make a little bit more money for his operation, but also with the mind to the environmental side of this, that these individuals need to have some awareness of what are the potential impacts of mismanagement of nutrients for crop production. So I spend a fair amount of time traveling the state doing those kinds of education events. I do have a research appointment with OARDC, which is the research arm of Ohio State University, and we do a fair amount of field research, primarily on the agronomic crop side, but I also conduct research in more the environmental side, and manure is a pretty easy field to get into on the research side. There's some money there, and we've been fortunate enough to get some funding from NRCS and Ohio EPA and US EPA, and that's part of what I'm going to be talking about today as one of the projects that they have funded. And just as a title, and I know this is rather lengthy, we've actually given this at national meetings, and the first comment for most individuals is, you probably should shorten the title, but I haven't really come up with a more efficient way of setting up what we're actually going to be talking about. So what we're going to go with is the effectiveness of field edge setback to reduce nutrient transport from manure application to frozen snow-covered fields. I do want to acknowledge the two individuals that I have listed with my name as far as the presenters this afternoon. Clayton Dygert is actually my research technician. He has done the majority of the field work. I'm typically involved in the design. He bounces ideas off me as far as how we're going to implement things at the field level. But he's ultimately the one that's responsible for the bulk of the work that we're going to be talking about today. And then John Roush is one of my colleagues. He's actually down there in Columbus. He's in the engineering department. He and I actually came up with this original idea and proposed this project to NRCS after they originally approached us. So just as an introduction, and we're going to spend the bulk of this afternoon talking about the project itself and more importantly, talking about what we've learned and how this is going to impact how we manage nutrient applications or manure applications to frozen or snow-covered fields. And obviously, I suspect that I recognize a lot of the individuals that are joining us on the call this afternoon. As most of you know, and for those who may be relatively new into this field, it makes total sense that the application of any kind of a nutrient, not necessarily just a manure nutrient, this goes for commercial fertilizers as well, that application of those nutrients to frozen snow-covered fields does represent a risk when we start talking about surface thaw early in the spring, when we have a lot of snow out on there and we get that thaw event and we get a tremendous amount of surface transport of that water and subsequently any of the nutrients that are contained with that represents a pretty significant risk to surface water quality. So it's obviously something that we're concerned with. And then the next logical question is, how can we manage that application to mitigate that risk of transport? And that's essentially what we've gone and done within this research project is, okay, there are certain guidelines presently in place. And again, I suspect that the majority of the individuals on the call are at least have a cursory knowledge of the document 633, which is the NRCS practice standard for manure application. Probably familiar with the section that deals specifically with manure applications to frozen snow-covered ground. There are certain recommendations that NRCS has in place to mitigate some of that nutrient transport, and one of those, strangely enough, is the observation of a setback, that being a 200-foot setback, that they have established as a best management practice, if you will, to mitigate that transport. And that ultimately was the objective for this study. Now, the one thing that you do need to keep in mind with how we actually did the work is we were following other 633 practice standards. Now, this wasn't just the 200-foot setback and we ignored the rest of the 633 document. What we were ultimately trying to test was that 633, more specifically the 200-foot setback portion of it. So we did observe the other recommendations that they have. The primary one the two primary that we really observed and they're really stressed in that is, if you can look at 633 section 7 point A, it discusses the application rates, the limits for application. Thou shalt not exceed 5,000 GPA of a liquid manure that's being applied to frozen snow-covered ground. That was observed. Our application rate was right at 5,000 gallons per acre. Additionally, they have in there under Section B that you should maintain or make the application on a field that has a minimum of 90% ground cover. That ground cover could be a previous corn crop, it could be a previous wheat crop, or it could be an application made to a cover crop. So those are the other two things that we observed and that we followed from that 633 document, but those were held constant across all treatments, and what we were really trying to observe and trying to evaluate was that 200-foot setback and how well it did at mitigating nutrient transport. And so that was the overall objective of the study. Just to give you a little bit of the field layout, we originally had proposed and put together a plan for this project back in 2006, and we got into it. We had visions of ISCO samplers and automated systems for actually collecting the samples and actually collecting subsets or subsamples of the main runoff events with those ISCO samplers. And we started doing a lot of evaluation of those samplers and started to realize pretty quickly they don't work really, really well for low flow events, which is what we're going to be dealing with at the small scale that we're testing. So those went out the window after the first year, but we had already invested 6 months into trying to see if we could get those systems to work and actually be implemented at the field level. And we were actually going to be purchasing additional units, and we realized that wasn't going to work. So we were set back a year, and then what we ultimately ended up with was a field that had a slope of slightly less than 2%. As Joe mentioned, I am an assistant professor within the academic system, which means I don't really have a lot of political clout. So I really can't select the ideal field that I would have liked to have selected for this project. So we were pretty much stuck with a field that had a slope it did have slope, and it was appreciable slope, but it was just under 2% using the clinometer method for determining the slope of the field. Not necessarily the best situation for us to really evaluate runoff. So one thing that when we get to the conclusions from this study, my suspicion is that the information that we've collected and what we've learned from this project is only really applicable to really relatively flat slopes. That doesn't make the research any less of importance, but it just means that we have to be a little bit careful what kind of inferences we draw from this kind of a study. So we didn't have much slope. We originally had a corn crop in there in '06. We had designs of coming in and making our application on that corn. The stover that was left, it's all being managed no-till, obviously. When we came back in '07, we had actually planted a bean crop, and we actually didn't take that to harvest, and a lot of the corn residue was gone by the time we come back in late fall of '07. So we decided to establish a cover crop for this particular year of the experiment, primarily because all of our corn residue was gone. And we did have that 90% ground cover. We actually seeded that, I believe it was late August, early September. We had a decent stand of fescue and ryegrass, got really good establishment, so we did reach that 90% ground cover that we're trying to achieve with that 633. Plot size, and this will be a little bit more evident when I show you a little schematic of the field layout. Plot size, they were 12 foot wide by 100 or 300 foot long, and I'll explain why we have two different distances when we actually look at the plots in the field, or at least we see a graphical representation of how the plots laid in the field. We used a dairy manure that was from an open lagoon. We have access to dairy manure here on the station. We have a dairy operation, and that's the pit that we used. It's an open pit, so the nutrient concentrations weren't necessarily that high, as you would expect from an open pit. Ammonium N was 24 pounds per acre is what the application rate turned out to be once we calculated our 5,000 GPA application. P2O5 was 11.5, and the K2O is 86.5, and we're going to be talking about K. We don't currently have any concerns about K environmentally, but there's a reason I use K within this study as far as documenting how those nutrients are transported down that slope. And again, we'll get into that a little bit later when we actually start looking at the data. For the 2008 study year, the manure was applied on January 28. If you recall what January of '08 looked like, it was a relatively warm winter at that point. We were getting concerned that we weren't actually going to get to frozen ground or even snow-covered ground, but we did have an opportunity in late January to make the application, and it was a good thing that we did because it was a little bit later until February before we got to frozen conditions again. So we were actually very lucky that we made that application when we did. Just a little bit on the plot layout and a little bit of a description of how these laid in the field. The orange areas that you recognize there are the areas that actually receive the manure application. Now, the reason we have the 300 and then the 100-foot strips is what we were interested in is what was the actual nutrient concentration going into that setback area. So that's the reason for the plots on the lower right where we don't observe a setback. We just have the application right up to the edge of the bucket collectors that you see at the bottom. And that was the justification for that, is we wanted to have a general idea of what was going into that buffer area, if you will, that 200-foot setback, and also to give us a comparison to what is the real risk if we don't observe the setback. What kind of potential concentrations can we observe going let's say directly into a surface stream or a surface waterway or something along those lines if we don't observe that setback, because that too was of importance to us from a research and even from an extension perspective. These were, each treatment was replicated 3 times, and the control areas, we do have soil test information. Just to give you some background, I didn't include that in this presentation. The phosphorus levels at this location are relatively low. I don't know how that might compare to a farmer's field, because farmer field levels are all over the place. These were in the high teens, lower 20s, with the exception of, and I don't necessarily have a good explanation for this other than historical management. The plots that don't have the setback, those on the lower right, plots 7 through 12, those actually had soil test P levels into the low 30s. My suspicion is someone at some point in the time, was doing some research out there, and maybe they made a phosphorus application that resulted in inflated soil test P levels in this area. Those levels aren't high enough to give me any cause for concern that it might have some potential implications on the study, because again, we're still talking about the low 30s. So it wasn't, although it was higher numerically from a research perspective, I'm not overly concerned that it's going to influence the observations that we made from those plots that had the higher soil test P levels. And that was just a little bit on the plot layout to give you a little bit of a feel for how these laid in the field. Here are some images to give you an even better idea of how we made these applications. Obviously, this is 2008 application. The field was frozen. Otherwise, the truck and the 400 gallons of manure that we're hauling on that flatbed trailer would have sunk into the soil relatively quickly. So we did reach frozen conditions. As you notice, we don't have much snowfall on the ground. Again, that was just a function of the year that we had in 2008, specifically January. This is actually a photo of Clay Digert, my research technician, out making the application. We actually had the yellow poly tank incremented, so we had an idea of about where we needed to be with our application. And this is, he calls this the Rambo gun that we use for the application, and he's going to cover that entire area. I'm the individual taking the picture, and as he progresses up the slope, I just pull the truck up and we cover that area with the approximate gallonage that we need to apply. And that, just to show you a little bit, these are the actual diverters at the bottom of the plots. We'll look at those a little bit closer here in a moment, where we actually collect the runoff samples and divert them into a channel, and then ultimately to a bucket collection system that we had to go with in lieu of the ISCO samplers. This, just to give you an idea of the plots that actually have the setback, this represents that 100-foot contributing area. We had lengthy discussions when we initiated this project. Do we need to have a larger size contributing area? Unfortunately, with the constraints that we had at this particular location, if you get much more in the fore of this photo, you're actually going to get to more flat ground, and we really don't have enough room from a research perspective to establish the plot. So 300 foot, unfortunately, was the max that I could work within the study. So by default, almost, we ended up with a 100-foot contributing area that goes into, as you can see in the background of the image, that is that 200-foot setback, and you can just barely make out at the edge of those plots the diverters, which is the gray tarpaulin material that we have at the end of those plots. And as you can tell, we didn't have much snow, and in fact, the application of that manure itself was enough to melt the bulk of the snow that we actually did have on the ground. And again, that was for 2008. I'm going to go forward just real quickly. These diverters that we have established in these are all graded so that they are slightly below the level of the plot itself. And they actually are channeled so that all the water should be diverted back to a piping system. This is a 4-inch PVC that actually runs into the bucket collectors. These are sunk into the ground, and you'll be able to see that a little bit better here with the image of the buckets. We have holes drilled. I can't actually find a hole in this one. There are holes drilled in the bottom, and there's holes drilled in the side. When you're dealing with a relatively flat slope, the biggest challenge we had was diverting the water from the sample that goes beyond what we actually want to collect. Now, we went low-tech within the study. Remember, we had designs on using ISCOs and automating the sampling procedure. In lieu of that, because number one, the ISCOs didn't work well with low flow. Number two, we would have had to run power to this location, would have been a bit of a challenge. and it would have been an additional cost that we wouldn't necessarily have been recouped within the study itself. So we ended up going with a low-tech approach, and this is that 4-inch PVC coming in from the diverter. It goes into the first bucket, and this is a pretty good graduate student question. For those who are more on the academic side, maybe you're serving on a graduate student committee, and they're doing anything with surface transport or doing any kind of field research on nutrient management and specifically water movement across the surface of a soil. Ask them how to collect a sample that's going to represent 5,000 GP, 5,000 gallons with only 3 buckets. And it turns out it's a pretty simple solution. This is actually devised by a researcher in Tennessee by the name of Daniel Yoder. Strangely enough, he is originally from the Worcester area. As most of you know, Worcester's got a relatively high concentration of Amish, and he, strangely enough, is of Amish descent. And he's the one that came up with this concept. And what we really have are these little triangles that you can sort of make out. There's 24 of them, equally spaced, equally sized. This has to be done with a laser cutter, and that's why they did it instead of us. Because they have to be relatively precise. This bucket has to be perfectly level, which we have to maintain in the field. We actually have leveling triangles for each one of the buckets. So what we ultimately end up with is when this bucket starts to fill up, we're going to collect 1/24th of the overflow and divert that into the second bucket. And that's ultimately how we come up with what we're trying to do was calculate total loads. There's some problems with total loads when we start doing small plot research that we may have time for at the very end. But this is ultimately how we collected our samples. This is a photo of the actual diverter, and as you can see, we have this sunk below the surface of the plots, and we actually have this back channeled so that we at least minimize the risk of water crawling underneath the actual diverter itself. So these are back channeled. There's an angle iron that runs about 8 inches to a foot below the surface of the plot, so that we minimize the actual potential of loss of sample because it actually got around our diverter. One more thing I will point out is that each of these plots was separated by an actual soil border. We had designs on making a metal border or a plastic diverter. We actually had plastic in about half the plots and realized that wasn't going to work very well because of the heaving issues that we have. That plastic essentially just lifts. So this turned out to be the best method for us to actually avoid cross-contamination of plots. And I'm actually quite glad that we didn't go the plastic or the metal route because of the issues that we did have with frost heaving at this particular location. Each one of these diverters is actually sunk into the ground about 3 foot. Because the first year we did this, we actually had some problems with heaving. We went in and made some adjustments to the infrastructure to get around those problems. So you've got a pretty good background on how we set up this experiment, and I always feel that's very important. Everything that we do on a research basis always has to have some sort of a context. It doesn't apply to everything, and I'm just trying to provide you as much background information about what we did so you understand how we make our inferences from that project, because we can't apply this to everything. A little bit on the weather data we actually have, and I think there's an image of it right there. You can see the weather monitoring station. This is just a simple watchdog weather monitoring station that we have located at the field experiment. We do not rely on the Worcester campus for the weather data because there's so much micro variability in climate that we want to actually have something that's right there at the field experiment. This just gives you a pretty good idea of soil temperature. That's represented by the red lines, and that's going to be following on the first vertical axis. On the second vertical axis is going to be our rainfall. That's going to be the blue line that you see at the bottom, and then the gray is the air temperature. And then what I've also provided are the sampling dates. Now, with this kind of a project, it would have been very nice if we could have had ISCO. We could have had, again, we could have characterized the runoff events individually rather than what we are left with here, which is it's sort of a bulk approach. We can't separate out first flush or first flow associated with a runoff event. All we can do is characterize the event itself. So we have a couple of different sampling dates. Now, there were other sampling dates within this. Those other sampling dates were either relatively small. We have to come to some agreement as to what we're going to consider a runoff event. Is collection of a less than a quarter of a bucket enough for us to go out there and sample? And so we ultimately decided that, you know what, we're going to have to wait till there's an appreciable enough runoff to make it worth our effort to get out there and sample that runoff. So, and again, that was just part of the protocol that we established for this particular experiment. As I stated before, we actually had some cooler temperatures in January, but we never really got to frozen ground until late January, and you can see that with the soil temp, which is the red line. At least it may have been frozen at the surface, but it wasn't frozen enough for us to actually get the equipment out into the field. We actually reached that in late January. We make the application January 28th, and then what happens with air temperature and soil temperature? We get a nice spike in early February. This to me represents sort of a worst case scenario. Not only did we have a spike in soil temperature, so we start seeing some thawing of the surface, but we also start to see the air temperature rise, and then we get a rather significant rainfall event. And that was not snowfall, that was a rainfall event. Actually, it was sort of a mix, but the bulk of it was actually rain. It wasn't snow, and that was approaching or slightly over an inch and a half. That to me represented worst case scenario for transport. We have a sample that we collected from each one of those plots that represented that actual runoff event. And then you notice we have another spike. We have a decent rainfall event in mid-January, or I'm sorry, mid-February. That was more of a sleet, slush. There was some snow with that event. So the actual amount of that transported, we really didn't see that until later in February when we were actually out there collecting our next sample. And this is sort of how the sampling went in 2008. Again, for me, it represented worst case scenario, with the exception of we didn't have a whole lot of snowfall on the ground when we made the application. This might have been a little bit different if we had had the same sort of situation that we observed in 2009, which we'll get to a little bit later. So this is when the samples were collected, and this is sort of the weather events, the weather pattern that we faced in 2008. Jumping right into the data, this is February 8th. That's that first sample collection that we had. And this is going to be conserved throughout the remainder of these slides. This is going to be the general look of how I'm going to represent the data. We're going to have the no setback, the manure. So we made the manure application, that 5,000 GPA, but we don't have that setback. That would be that 100-foot treatment. And then we have the no setback, no manure. So we didn't make an application of the manure, and we're not observing a setback. Then we have the setback where we made the manure application, and then the setback where we made no manure application. And interesting to me was with this first application event, typically when we think about dairy manure or any kind of a liquid manure, we very rarely have much in the way of nitrogen, just because it's in order for us to create nitrogen or nitrate nitrogen, it requires some oxygen. It's a biological process. We don't actually, usually those levels are below detection. We do see some nitrate nitrogen. What's interesting is that it's coming from all plots, so it wasn't necessarily associated with the manure application. I don't know if that was, my only possible explanation is that is some residual associated with the fertilization of the previous crop that we may have had out there, and maybe some of that comes from the rainfall, but those concentrations are relatively high for if we're going to just explain it with rainfall. Statistically speaking, though, again, this was a research project, so I'm more interested in the statistical inferences from this kind of a study. Statistically speaking, there were no differences between the treatments, either with regard to nitrate nitrogen or what I'm more interested in, the ammonium nitrate nitrogen, which is very interesting because I would have suspected with the runoff event that we had that there would have been some ammonium nitrogen that ran off from those plots that we would have picked up from that manure application, specifically looking at that first no setback manure treatment. But interesting, we didn't pick it up. This could have been an artifact of the way we sampled it with that first application. Ammonium doesn't necessarily stick around. There is a gas exchange between ammonium and ammonia when we're talking about a static sampling like this. So this might simply be explained by we just didn't get out there, air temperature got a little bit warmer, and we lost some of that ammonia from that plot, and it ended up being below detection for the actual methodology that we used in the lab. So from that first application, that first runoff treatment, we didn't pick up anything with ammonium. I want you to keep that in mind because we do start noticing it later with subsequent samplings. Looking at the DRP, just to make you aware of my nomenclature, that's dissolved reactive phosphorus. That's actually phosphate phosphorus, which is more of concern for us environmentally, at least, as far as what could potentially be utilized by an aquatic plant species. Total P is more representative of the DRP plus the particulate P that we had in those samples when they were transported. Just to give you some additional background on information on how these were sampled, we did filter these right after sampling, so the particulate P shouldn't have had much time to equilibrate to DRP. Now, that doesn't mean that didn't occur with those samples sitting in the field because this was a static sampling. We may not have been out there right after the runoff event occurred. There was likely some lag, and in fact, I know for the bulk of our sampling, there's a little bit of a lag time. So this DRP might be a little bit inflated because some of that particulate-bound phosphorus may have an opportunity to actually go into solution and be reflected in the DRP. But just statistically speaking, there were differences, and as you would expect, this is what we would have expected when we established this experiment, that when we don't observe the setback, we have a much greater risk, and that risk was realized within this experiment, of transport of the DRP and the total P, the phosphate P, or the DRP being represented by the gray bar, the total P is the scarlet. We do have more phosphorus being transported when we don't observe a setback. That should not be of surprise to any of us out there in the real world that actually do any of this sampling. Does the setback do its job with that first application or that first runoff event? Do we see any increase where we observe the setback? And the answer is no. Those treatments look very similar to where we don't apply any manure at all, which again tells us, at least for that first runoff event, that setback is doing its job. Now, I mentioned earlier that we did manage, or not manage, but we did monitor the K levels. There's a specific reason that I did the K. The rationale behind that is the K concentrations were relatively high in that manure, and subsequently the amount of K that we supplied to that field was high. So my suspicion is if we're going to see nutrient transport, it would be easier for me to identify that with that K application just by because the concentrations were higher. The other reason I'm interested in K is, unlike P, we don't have to worry as much about phosphorus nutrient interaction with soil and other chemical species out there. When we deal with phosphorus, we have to deal with precipitation and absorption reactions. With K, all I really have to be concerned with is absorption, and that really isn't that big of a player if we're talking about a soil that's relatively frozen or approaching frozen conditions, because that material is simply just going to move across the surface. It's not really going to have anywhere to go. So I kind of use K as a tracer within this study because I can draw inferences from K that I may not be able to draw from the P. And when we look at the actual K concentrations coming from the first runoff event where we don't observe the setback and we made that manure application, as you would expect, we have relatively high K concentrations. Again, does the setback do its job with regard to K? And the answer is yes. There's no statistical difference between the setback where I applied the manure and where I didn't apply the manure. We're right at the edge of a statistical significance between the setback, but my suspicion is that's just an artifact of the soil test levels, and not necessarily something that's the result of the actual experiment itself. I'm drawing more inference from that observation that no setback. Hey, guess what? I do have transport of the nutrients contained in that manure, and if I observe the setback, we don't see that. Moving on to the second sampling, and again, as I mentioned in the previous runoff event, that was February 8th, we didn't observe much in the way of an ammonium difference, but what do we notice here? Now, the one thing you have to be a little bit cognizant of, I am a statistician, and we have tremendous variability between these plots. We have microtopography that I'm having to deal with. We didn't grade these plots prior to establishment of the experiment. That would have been more cost than we could have rationalized or justified when we're going after the money to do this work. So the LSD levels are quite high. That doesn't keep me from making the inference that the trend was that when we don't observe the setback, our ammonium concentrations are north of 20 part per million. That is way, way, way too high. Do I see that same kind of a spike if I observe that setback and I make that manure application? And the answer is no. It looks very similar to the other treatments that don't receive any manure. And again, with the realization that there is going to be some variability. So at least numerically and as a trend, boy, that 20 part per million is a really, really high number that really concerns me if I'm dealing with a manure application and I don't observe a setback. Now we get into the phosphorus, and the phosphorus looks very similar to what we observed with the first application. The phosphate P levels are right on the edge of statistical significance when we compare that to the no setback no manure. It is statistically significant if I compare that to the setback with the manure. And again, for me, that's ultimately the comparison that I want to make. These others are just in here for a control and additional observations that maybe there's something going on that we can't necessarily explain. But at least for me, comparing the no setback with the manure to the setback where I also applied the manure, I'm seeing very high significant differences between those treatments. So again, if I don't observe the setback, I have a very high risk of nutrient transport away from that field. Not something that any of us would recommend. And the setback does appear to be doing its job with regard to phosphorus. What about the K? How does that story look? It looks as we would suspect based upon the other observations that the K being transported down that slope is really, really high, but if I observe that setback, it's not making its way to that diverter and ultimately to the collector. So again, same inference. We don't observe the setback, huge risk of transport, and that risk is being realized. If I observe that setback, that's behaving to the other treatments, behaving similarly to the other treatments that don't actually receive an application. Let's continue following this into March. This is March 17. We really are seeing a very noticeable effect. Again, 25 part per million ammonium nitrogen concentration in the runoff coming from that plot that received manure where we don't observe a setback. Statistically, that is a valid number. Is the setback performing its job still? And the answer is yes. We're still not seeing much in the way of ammonia being transported from the plot that received manure, but we observe the setback. Looking at the DRP and the TP, the image is becoming a little bit clearer. We noticed it in the first two applications, or the first two runoff measurements, excuse me. It's still there. Where we don't observe that setback, we have a tremendous amount of P being transported. If I observe the setback, we don't observe that. Moving on to K, it's the same story. Okay, so the first year's inferences, and let's go ahead and let's just stop right there. From the first three runoff events, the conclusion would be at this point that yes, the setback is doing its job. We are seeing a relatively high concentration of nutrients flowing into the setback area. We're not picking it up at the end of the plot where we have the collectors. So is that the end of the story? Well, the answer is no. We continued to sample these whenever we had a runoff event. This is getting into early April now, so we're actually approaching planting season, or when producers are thinking about planting corn. And what do we start to notice? Where we don't observe the setback and we have that manure application, we still have relatively high concentrations of ammonium. But what are you starting to notice where we applied the manure and we still have the setback? We're starting to notice that number creep up. So what do we at least think is transpiring is that manure material and some of the nutrients contained in are slowly making their way down that slope, and over time they are eventually going to make their way to that diverter. Okay, now what is of importance here is that the total load, even though they're starting to make their way down slope, the total load or the total amount of ammonium being delivered is going to be substantially less because we've delayed that application and we have allowed for more retention of the nutrients that we supplied. It's not going to be an indefinite fix, but we have certainly decreased the total load, or the total load of nutrients being delivered down slope. Again, we noticed this as well with the DRP and the total P. Those numbers from that setback, even where we applied the manure, are starting to creep up and are getting at least close to the concentrations that we observe where we don't have the setback and we applied that manure material. Again, the total load that's going to be delivered is going to be substantially less, but we are eventually going to reach a point where those nutrients are going to find their way down slope, and I think that's what we're getting an indication of. We also see that with K. So from the first year, what have we learned is that essentially what we do with the observation of that setback is we're buying time it's a physical barrier to transport of that material down slope. If we don't observe the setback, there's no mitigation of the nutrients coming off. They just go straight into whatever we're not observing as far as setback. That could be a surface waterway, could be a surface stream, surface pond, whatever the case may be. If we don't observe the setback, the total load is going to be relatively high relatively quickly. But if we do observe the setback, we're essentially buying time and decreasing the total amount of nutrient, the total load that's being delivered to a surface water. And that's essentially what we, from the first year, that's the inferences that we take away. We repeated this in 2009, same general experiment. The difference was we did plant corn in May of 2008, so we're no longer dealing with an actively growing cover crop out there. We're actually dealing with a residue from a corn plot. The application rates were the same. It was still the 5,000 GPA. It was applied January 23rd, 2009. Nutrient concentrations, strangely enough, are about the same as they were in 2008. Application conditions were a little bit different for those of you who recall what this past year was like. Unlike 2008, where we had very little snow cover on the ground, this past year when we made the application, we had greater than 7 inches on the soil surface when we made the application. And as you notice, you can see the corn stalks from the previous corn crop. Obviously, everything was maintained no-till. We muddied up the snow pretty nicely. If you want to call that mud, that would probably be used. Another term would probably be slightly more appropriate. So the application conditions comparing 2008 to 2009 completely different, primarily because of environment. If you recall what this past winter was like, relatively cold here in Northeast Ohio. Soil temps hovered right around zero for the bulk of the year until we actually got into March. We didn't have those rainfall events that we had actually observed in 2008, and in fact, the bulk of these events that represented in the rainfall, the precipitation amount, are primarily in the form of snow. So not necessarily a worst case scenario for transport unless you consider the surface thaw and the snow thaw and then the subsequent runoff event. And for those who recall, this past year, specifically in northeastern Ohio, from that runoff event, we had a great deal of flooding in this part of the world. So we didn't have the combination of rainfall, but we did have a lot more snow cover out on the ground. So our runoff event was still quite substantial, even though we didn't get much in the way of rainfall. We have 2 sampling events relatively close, primarily associated with a thaw event. So it's a slightly different type of a runoff event. And so we jump right in. February 10th, that application was made January 23, excuse me. We come back February 10. Again, we're seeing that nitrate spike. Again, I can't attribute that to the manure application. We did fertilize that corn crop. Perhaps this is just a symptom of the actual application itself and some of the residual nitrate. What I'm more interested in is the ammonium in. We did the nitrate in because we had the samples and we went ahead and analyzed them anyway. We look at the ammonium in. It looks like there's a spike where we have the setback and we did apply the manure. But that, statistically speaking, there weren't any differences. There's a tremendous amount of variability with that first sampling event for ammonium. We start looking at total P. Again, at least visually, it's very striking that where we observe the setback and we applied the manure, we have a high amount of phosphate P and total P. Statistically, there's not any differences in those levels. While they are relatively high, I'm still not overly concerned at this point that it's necessarily related to treatment. It may be, but it's hard for me to make that inference if I'm applying some sort of a statistical methodology. Looking at K actually follows what we would have expected. Where we don't observe the setback, we make the manure application, we have a really, really high spike in potassium. Where we observe the setback and we made the manure application, we don't see that. Again, this is more in line with what I would expect with nutrient transport down those slopes. Second sampling event, ammonium concentrations from all treatments are relatively high. Statistically, there weren't any differences. We do see a higher value where we don't observe the setback, but I also see that where I didn't apply any manure at all. So I'm at a little bit of a loss as to why that looks like it's a spike, although it could possibly be, and this is a bit of a stretch, that some of that ammonium was still around from that fertilization pass when we're talking about the corn crop. My suspicion is that's probably pretty small, because that once we get into relatively warm soil conditions, all that ammonium goes to nitrate pretty rapidly. So I think this is just not related to treatment at all. I think it's just a simple fact of the experiment and what we observed as far as ammonium transport. Looking at the DRP and the total P levels, what we do notice is that the total P delivery was was relatively high when we didn't observe the setback, and that was statistically significant. But what is of interest to me, specifically with the second sampling data, is that runoff event was pretty sizable. Between February 10, February 12, we got relatively warm air temperatures, a lot of snow melt, and a lot of surface movement of the snow, and more specifically the water that was melting from that snow. Look at the actual levels, the concentrations that we observed. These are north of 15 part per million, even when I didn't supply any manure. And one thing that we often talk about when we talk about specifically manure management or nutrient management in general and the potential environmental implications is we always talk about the source side of that equation. And it's primarily because there's something that we can do about the source side. We can minimize the risk, and notice I use the term risk. We can minimize the risk of nutrient transport by doing a better job of supplementing nutrients, making the application where they're warranted, things of that nature. But occasionally we run into this instance where the transport side of that equation was so great that even though our soil test P levels and it didn't receive any fertilization at all, we still got a huge amount of P being transported. And again, that to me is that take-home message that we can do so much on the source side, but unfortunately, occasionally we're going to get these instances where the transport is going to really dictate how much nutrient loss we observe. The other thing to take note of is that the phosphorus levels, or the DRP levels, were approaching 5 part per million. That is a very high concentration. And again, it's not something that we typically see, specifically in the instances of these plots that receive no manure. Those have not received any phosphorus fertilization for a number of years, and the phosphorus soil test levels are relatively low, but we're still observing a high amount of phosphate P being delivered. And again, that's just an illustration of if we have that huge transport event, no matter how low our source side on that equation is, we can still see some loss. The K, again, sort of tells the same story. Very high nutrient loss levels from those plots. A bit of a trend. Statistically, there weren't any differences when we compare that no setback to that received manure to the plot where we observed the setback. Moving on to March 11, we're starting to get a little. It seems like the further we get away from the large runoff events. So these are more. I'm going to claim that these are a little bit more due to rainfall as opposed to the thaw event, although based upon 2009, my suspicion is this is still a portion of that thaw event just because of the amount of snowfall and how cold we were. Seems like when we start getting into those March samplings, we start to get a clearer picture of what's actually going on within the plots. This was illustrated in the previous year as well. We look at that where we don't observe the setback, we make the manure application. Relatively high ammonium concentrations, not near at the magnitude that we were with the earlier runoff events. We compare that to where we observe the setback, we make the manure application. Again, is the setback doing its job? At least in that March 11 sampling, it appears that it is. Same story with that DRP and the total P. Where we observe the setback, we see lower concentrations compared to. Important to take-home message from this project as any is you've got to manage the application so as to avoid application right up to the field edge, because we know that this can happen. Looking at K levels, same story. Where we don't observe the setback, we apply the manure. Relatively high concentrations where we observe the setback, and we make that manure application. Statistically speaking, we're right at the edge of being significant. Is the observation of that setback doing its job? And the answer at this point with this sampling is yes. Now, we don't have subsequent sampling data from. We actually do have in April. We're rerunning that data right now, and I have not got that information back. So let's talk about some general conclusions that we can make from this study. And this is where we're going to leave it this afternoon, then I do want to open it up for questions. From this kind of a project, does the observation of a setback distance do its job as far as mitigating nutrient transport? And I think the take-home message is it does early. So I think the general conclusion would be that the observation of that setback is going to do a relatively good job of decreasing the total load of nutrient being delivered associated with that manure application. It doesn't imply that it's going to be a long-term fix and that you're not going to get some nutrient delivery, because I think we observed that in 2000 with that April 2008 sampling. That's the one thing I really take from that. Now, the one thing you have to consider when we talk about this kind of a project is this only applies to the slopes that we tested within this study. So this is only going to have uh, general. The general inference can only be applied to fields that have a relatively flat slope or slopes less than 2%. When we start talking about a 5% slope, my general thought is this. If we start dealing with 5 or 6%, and if you start getting into 6%, there's other considerations to be made within that 633 document. If we start approaching that 6% limit, my suspicion is that the delay, the amount of time we're delaying nutrient transport to the edge of the field is going to be shortened. So as opposed to what we had within this study with the kind of runoff events that we observed for the 2 years of this study, we're talking about upwards of 2.5 months. I don't know if you're going to have that much time. It's still likely to have an impact on the total load of nutrient from that manure application, but it's not going to have as high an impact as we observed with this 2%. And again, this only applies to what we followed within the other 633 guidelines. As a standalone, that 200-foot setback may not have the same utility if you put on 15,000 or 20,000 GPA as far as an application rate. You're likely to speed up the process of nutrient transport down that slope just because of concentration. And with that, I will try to entertain any questions. I hope you found this of interest. We're actually going to be in talks about maybe expanding this project to a steeper slope to determine the utility of those 200-foot setbacks on, say, 5% or something that exceeds 5%. But we haven't got that nailed down as of this date. Any questions?
Okay, folks, if you have questions, you can type them into the chat box down in the lower right-hand corner.
And like Joe mentioned, if you think of something later, here's the first question. Does the soil type matter? That's an interesting question that I actually haven't thought of. It's likely to, and I'm not sure how much it matters with an application on frozen ground, because when you're dealing with the frozen ground, soil type goes out the window because infiltration is going to be minimal across all soil types. Now, it might have influence on subsequent runoff events if you're dealing with a poorly drained soil compared to a moderately well-drained or a well-drained soil. Let me state this about this particular field location. This field location is moderately well-drained. This is a Worcester Canfield soil. So we do have some clay, but it is relatively well-drained. If I did this on, let's say, a Hoytville clay loam or a Blount or something that's got a heavier clay material, am I likely to see different types of observations? My suspicion is not on the early runoffs, because even though the surface layer is starting to thaw, I've still probably got at least a little bit of subsurface frozen ground, so the infiltration rate is going to be low across all soil types. But when we start getting into March and April, I might have a different inference. I might have a different observation, and that's a great question. Any other question? And
Robert, I have one for you. Are there any specifications in the recommendations as far as what would be in that setback area? I mean, your test was basically setback on a plow or on the actual, productive part of the field, but I assume that it would make a big difference as to whether or not that setback included, say, a filter strip before surface drainage.
It doesn't specify if you go to that 633. All it states is that the area be maintained with at least 90% residue cover. It doesn't make allowances, or it doesn't state explicitly that you need to have filter strips or some sort of or vegetated filter prior to interface with a surface water. It just says it has to be 90% ground cover.
But
and that's ultimately something we could eventually test in a project. That wasn't obviously something that we were testing within this study.
Yeah.
And to be honest, my suspicion is that would have greater influence on the later runoff events as opposed to the early. Those runoff events that we would have observed in January and February probably wouldn't be too influenced. And the reason I say that is because in 2008, when we first did this project, we basically had a vegetated filter out there. That was the cover crop, the rye fescue that we had established. So my suspicion is that if we had a filter strip beyond that, it probably wouldn't have made much of a difference. Now, if you go to 2009, again, early on, I don't think you're going to see much of a difference, but for the later application or for the later runoff events, you know what? You might start seeing a difference if you do observe a filter strip or some sort of a vegetated buffer outside of that 200-foot setback area. You might start seeing differences associated with that. Oh, there's a great question from the Ohio USGS. What percent of people out there follow the setback guidelines? That would be a better question maybe for someone from NRCS. They are they're not the enforcers per se. I'm certainly not an enforcer with Ohio State University. We're more of providing guidelines or BMPs. I don't have an idea. I will say this: if they are a part of an EQIP program or if they receive any NRCS dollars, they are supposed to follow 590 and 633 practice standards. For those individuals who fall outside the purview of EQIP, or if they don't receive any NRCS dollars and are not a permitted facility, they are not subject to these rules. So as far as what percent, boy, in a perfect world, I'd like to see say the majority, but I honestly don't have a clue. And maybe I know there's some NRCS folks on here, Jocelyn and some of the other folks. Maybe they have a better feel for what percentage of folks actually follow those guidelines. Other question? Could this project be replicated in Northwest Ohio? Great question. It could. The challenge that we would have from a research perspective is we do have a research farm in Northwest Ohio, but they don't have any appreciable slope. So that would actually require some sort of a grading. Now, if we did this on a farmer's field, that would be a possibility. But with the type of project, and that was part of the rationale for locating it here, at least originally, is it's rather time consuming. And a lot of labor goes into plot establishment and plot maintenance and collection of samples. So that this could potentially be replicated in other parts of Ohio beyond Northeast. As far as project cost, it really depends upon a couple of things. The bucket system itself and the diverters are relatively low cost. They're not tremendously expensive. The real challenge that we had here is we had additional costs with an installation of a drainage system because I had nowhere else for this water to go. So if you can get it into a 5% slope, you won't have to deal with that. You'll probably be able to set the bucket collectors above soil level and not have to deal with a subsurface drainage system. My off the cuff thinking labor, materials, this probably cost us $20 to $25 grand just for infrastructure. That includes labor and materials. Actually, if I really throw labor, it's probably closer to $35,000. And part of that was design. We spent a lot of time designing this and making it work within that field location. And just to let you know, NRCS and EPA both ponied up $50 grand for this project. And their funding is greatly appreciated, without which we could have never done this, because it's a large project to try to get on its feet. It's just a lot of cost up front.
Well, I think we're right on the end of our time window. So, Robert, I want to thank you for putting together the presentation and being part of this. And Robert, if you can type in your email address and phone number if you want to, then people who have more questions can get in touch with you. And Brian just pasted in a link to the evaluation for this webinar. If you would, all the participants can click on that link. It's a really quick evaluation. I think it probably takes less than a minute to do it, and that helps us to know what you liked and didn't like. If there were any technical issues that caused you problems, it will help us to do a better job in the future. So thanks everyone for being on, and thanks again, Robert, for the great presentation and sharing your knowledge with us. And
I certainly appreciate it. Thank you for the opportunity.
okay.